Okay, this is lecture 19, and today this is going to be the last sort of technical lecture of the class. Then this next lecture will be I'll give a talk about phase transitions in fluid turbulence. I don't think I'm going to get to anything extra uh, today. So today we're just going to finish the calculation of the epsilon expansion, and let me explain that to you. Okay, so let me just recap for you what we did last time. And again, this will be the most technical, boring, uninspiring lecture of the entire course. We're just going to show you how to walk through the calculation, show you that it's conceptually the same as everything that you've seen before in the simpler normalization group that's in real space. So we're just going to go through that because I know some of you are interested in getting a guideline to the technical details. From this lecture, you won't get technical mastery of how to do these calculations. You will have to go through chapter 12 of my notes, my book, but this will give you the guideposts to how to understand that for those of you who want to do that. Okay, so let's go back to what we want to solve. So that's looking on the right-hand panel. The problem we're trying to solve is just the effective Hamiltonian for the quartic Landau free energy. And what we did was step one, which is in section 12.2 of my book, is the Gaussian model. So we set u and h equal to 0. So now we have a Hamiltonian which is just quadratic. And as you remember from elementary statistical mechanics, if you have a Hamiltonian which is quadratic in its degrees of freedom, it is exactly solvable. It's just a harmonic oscillator. So we know that this is going to be exactly solvable, and we're going to go through that. So what we're going to do is later we will treat the quartic term, the interactions, as a perturbation. So now we're just going to sort of grind through the machinery of how to distinguish the long and short wavelength modes and how to deal with them. So over here then, on the right-hand side, we have the effective Hamiltonian now in K-space and with a quartic term removed. We have two components. There's long wavelength ones, are the degrees of freedom, which are between naught and lambda over L. And the short wavelength degrees of freedom are between lambda over L and lambda. So lambda over L being less than K is less than lambda is looking at the short wavelength degrees of freedom, which is like looking inside a block spin in our real space in a picture. What we're going to do is we're going to integrate out the short wavelength degrees of freedom. We're calling those sigma, just like we did before. And when we do that, the Hamiltonian is going to be additive, and therefore the partition function is going to be the product of a partition function for the long wavelength, Zs, and a partition function for the short wavelength, Z sigma. And when we do the integral for Z sigma, you get what is down here. You get this quantity e to the half times the sum over k modes, the high wavelength modes, this logarithmic function of k. And it's just a number, and there's no infinities or anything in that, so it's just some numbers. The long wavelength part is shown below, and everything about that looks just like the original Hamiltonian, except that the range of k goes from naught to lambda over L. And so that's the problem that we need to solve. So that's step two. To compare with the original problem, we need to have naught is less than k is less than lambda, not naught is less than k is less than lambda over L. So it's very simple. All we have to do is redefine k. It's just a dummy variable. It's just a label. So we just rescale k. So we're going to define a new k, which is k sub L. That is just L times k. And we choose that so that when k is equal to lambda over L, the new k is just equal to lambda. And once that's the case, then that means that the sum is going to be over k modes that now go up to naught to lambda, which is what we want. But it's more complicated than that. And the reason it's more complicated than that is because the field S, the field that we're integrating over, itself has dimensions. It goes as L to the power 1 minus D over 2. So when we rescale space to fix our K problem, that means that the field is also going to change. And so how is it going to change? Well, we'll write it as changing like this. We take the original field, and now what we're going to do is say we get a new field, S sub L, which is related to the original field by what is called a wave function renormalization constant, which I've written down as little z, not to be confused with the partition function. And then what do? We choose that coefficient, that little z, in such a way that when we write down the new rescaled Hamiltonian in terms of this new field, the coefficient of the gradient term is equal to a half. That's how we're going to, each time we do a renormalization group transformation, we're going to insist that the coefficient of grad S squared is a half. And why we do that? Because then we can just read off how the coupling constants in the Hamiltonian, the effective Hamiltonian, are changing under successive renormalization group transformations. So then we substitute that in, and we get the formula shown in step 3. So we get that, and then we define this term in brackets here. We define that to be RL plus KL squared, and so we can then read off that RL is just L squared times R naught. And that's the one step of the renormalization group. So we've integrated out the short wavelength degrees of freedom. We've rescaled the field or renormalized the field, and then we've read off how the coupling constants have transformed, and that's just a very simple recursion relation, and nothing special happens with that. Nothing complicated happens with that. Okay, that's not going to be true for the next stuff. Next thing that's going to happen is going to be very complicated. Okay, but it's easy to understand, so let's get into it. So the problem with the Gaussian model is everything is just quadratic, but there's no spontaneous symmetry breaking. So what we want to do now is we want to put in the symmetry breaking. So the next thing we're going to do is we go back to our Landau theory or our effective Hamiltonian. We had originally R naught S squared plus the gradient terms. Now we're putting in the 1/4 U naught S to the 4th term. And we know that in the equilibrium, the Landau free energy is minimized. And so that means that either S is equal to 0, differentiating that, or S squared is equal to minus R naught over U naught. And this is the solution this is the important solution when R naught is greater than 0. And this is the solution when R naught is negative. Of course, S equals 0 will still work as well, but it's not going to be the one that breaks symmetry. So now what we're going to do is, the next thing is we're going to do perturbation theory in U naught. And we already know from what we discussed last week that this perturbation theory is doomed to fail. It's doomed to fail because we know that the small parameter is not really a usable small parameter, and that U naught will scale and it will blow up as we go towards the phase transition. And so this perturbation theory is doomed to fail. And we're going to get around that by a dirty trick. The dirty trick is that we're going to then do all the calculations in non-integer dimensions. And that's the trick that we're going to use. So now we're going to formulate the problem like this. So my Hamiltonian, let me just give you the reference before I write that down. Okay, just so that when you want to look this up, those of you who want to learn how to do this, so the reference is my book, and this is section 12.3.1 and the following sections. Okay, so let's now write down the problem as we want to do it. I'm going to write down my effective Hamiltonian as the integral dr, and then 1/2 grad S squared plus 1/2 R naught S squared plus 1/4 U naught S to the fourth, and then minus H naught S when we want to put in an external magnetic field. We're going to have naught is less than K is less than lambda. And so therefore S of R has no Fourier components larger than K, than lambda. Like that. I'm going to introduce a notation that we're going to desperately need. So when I write down this, I'm going to write that as an integral. That is going to mean, that's shorthand for the integral from naught to lambda d dk over 2 pi to the power d. So that's how I'm defining that. And there's another notation that I use, which I want to mention, which is I write it sometimes like this: naught to lambda d slash k. Okay, why that? Well, remember Planck's constant, h bar is h over 2 pi. So therefore, ddk, so d slash k is ddk over 2 pi to the power d. Okay, so that's just like h bar. Okay, so we're now going to write out what the Hamiltonian looks like. So when we do the Fourier transform, for minus h of s, what we're going to have to do is we're going to have to deal with this term, integral d dr s of r to the fourth power. Okay, now, when we didn't have this problem before, because we just had the quadratic term, s squared. And you know that when you have a s of r squared and you take the Fourier transform, it's just diagonal in k-space. That's why we use plane waves. S to the fourth is not diagonal in k-space, and this is where the problem is. So let's now write this down in Fourier transform. So it's going to look like this. First of all, I've got the integral d dr, and then what I've got is for every s variable, I have a Fourier transform. So I'm going to write the s variables like this. I'm going to do s of r as a Fourier transform, e to the I k dot r s hat of k. So what I'm going to get is the following. I'm going to get an integral k1, an integral k2, an integral k3, an integral k4. And then I'm going to get s of k1, s k2, s k3, s k4. I'm going to get 4 of those. Okay. Then I'm going to get all my factors of e to the I k dot r. So that's going to look like this. E to the I, well, let me do it in a different color. There's a reason I want to do this in a different color. So then I'm going to get e to the I, and then k1 dot r plus k2 dot r plus k3 dotted with r plus k4 dotted with r, like that. And the thing I want you to remember is that that if I write delta of x, remember that delta of x is just 1 over 2 pi integral from minus infinity to infinity e to the I kx. So that's the delta function. So therefore, when I do the integral over ddr, here's my integral ddr, and then here is my integral of a bunch of k's times r. So when I do that integral, what I'm going to get is a delta function. So let's now write that out. So then integral d dr s of r to the fourth is then going to equal the integral of k1 up to k4, those things, 2 pi to the d times a delta function of k1 plus k2 plus k3 plus k4 times my fields sk1, sk2, sk3, sk4. And this delta function there, you can see, says that the momenta have to add up to 0. And so we therefore think of this as a momentum conserving delta function. So this thing here is a momentum conserving delta function. And that's the fact that the k's are all related like that is one of the reasons why this term is not going to be diagonal. And that means that when we do the integrations, we are going to have a bunch of problems. Okay, so now let's write down what our Hamiltonian is in this language. So now minus the Hamiltonian as a function of the degrees of freedom is equal to 1/2 k r naught plus k squared times s of k squared. So that's the term that we had before in the Gaussian theory. And then then we have the quartic term. So we have 1/4 u naught. And then now the integral from k1 up to k4 s k1 up to s k4, and then 2 pi to the d times momentum conserving delta function. And that's the Hamiltonian. Okay, so all right, that's just the first part. Now the next step that we need to do, so that's that we can think of as being a step 1. Okay, so now step 2. So what we're going to do with step 2 is we're going to break the S field into SL prime plus sigma L, where SL prime is the long wavelength and sigma is the short wavelength. Now, here's why it's complicated. So in the Gaussian theory, where we didn't have any quartic terms, the S prime and sigma did not interact with each other. And that meant that they added into the Hamiltonian. That meant that the partition functions factorized, and so there was nothing complicated. But now what's going to happen is in the quartic case, what we are going to get in the full quartic Landau theory what we're going to get is s to the fourth is now going to be symbolically s prime plus sigma L, and there's going to be 4 of them, s prime plus sigma L, s prime plus sigma L, s prime plus sigma L. So there's going to be 4 of these things, and then when we multiply them out, we're going to get every combination of s's times sigmas. So then when we multiply this out, We get every possible combination of powers of S prime multiplying powers of sigma. And then we have to do the integration over the sigmas. So I'm going to go through and write down what those things are. But what that means is that we can see straight away that what that means is that the form of our effective Hamiltonian is going to look something like this. It's going to be minus an effective Hamiltonian just for the SL prime fields. It's going to be an effective Hamiltonian just for the short wavelength degrees of freedom, the sigmas. And then there's going to be another term, just like we had before in real space, where I now have an interaction between the SL primes and the sigmas. And so everything that we're going to do is going to be to compute that, that perturbation. So let's have a look and see how we do that. So if that's what the Hamiltonian looks like, then our partition function is now going to look something like this. It's now going to be a function of two variables, r and u, and it's going to look like this. It's going to be the integral of e to the h yeah, notice that I've defined yeah, I'm going to write it down like this, e to the h. Wait, I've got a confusing notation here. I think that in the way I'm defining this, I'm defining those to be pluses. Okay. Notice the pluses. Okay. I want to get rid of all the minus signs. So I've called it e to the plus h s prime. So, and then I have h sigma plus v of SL prime and sigma. So I've got to do that. And then I'm going to write this now as the integral d SL prime, the long wavelength part, acting on e to the h s prime, the Hamiltonian for the long wavelength part. And then that's going to be acting on the integration over the short wavelength degrees of freedom. And they are e to the h sigma plus v of s prime in sigma. Because if I'm looking at this as this variable, that's the dummy variable, it definitely occurs in here, but it also occurs in the interaction with the long wavelength degrees of freedom. So when I do this functional integral, let me close this thing here. So when I do this functional integral, which I'm going to do shortly, when we do this, this is going to be the result of doing this calculation will be some mass involving S L prime. So I'm going to get some, after I've done that, I'm going to get some big mass. It's going to involve the long wavelength degrees of freedom. And that big mass is then going to add to the part where the long wavelength degrees of freedom are just on their own. Okay, so that's the strategy. So we're going to have to now compute the functional integral in green. So let me now write down the steps, and then we're going to do these steps one by one. So the strategy then Step one is do the integral over all the sigmas. So we're going to do that integral. Then we're going to do the wave function renormalization for SL prime. We're going to rescale K to KL like that. And that's going to give us a partition function, which will now be a functional integral over DSL to some new effective Hamiltonian at the scale L. And from that effective Hamiltonian, which just involves the long wavelength degrees of freedom, once we have that, then we're going to use that to read off the recursion relations for our fields R and U. So that's the strategy. That's what we're going to do. Now remember what we did in real space. When we did this in real space, we defined when we did this in real space, we defined a sort of zeroth order average, which was just with respect to the unperturbed Hamiltonian. So we're going to do that here. So let me now write that down. So we're going to follow the strategy from real space RG. So what we're going to do is we're going to define an unperturbed uh, um, Hamiltonian and expectation value. So how do we do that? Well, I'm going to define the following. So like I did before, any variable, any function of the long wavelength degrees of freedom, average with respect to the short wavelength degrees of freedom. When I write that down, here's what I mean. I mean the integral, path integral, functional integral over the short wavelength degrees of freedom, the effective Hamiltonian of the short wavelength degrees of freedom, the sigmas, my quantity A, whatever it is, as a function of SL prime and sigma. And that's going to give me something. And then I'm going to normalize that by the integral of the partition function for the short wavelength degrees of freedom. So it's going to look like that. So that is the analog of taking an average of a bunch of spin variables inside a triangular block spin like we did in the real space RG, but now we're doing it for in K space rather than real space over a triangle. And so what that means is, so this thing over here, this denominator, this is just the partition function for the uh, the short wavelength degrees of freedom. And because we're integrating from lambda over L is less than lambda, a finite range of wave number space, this thing is going to be finite. So that's going to be just some number. So therefore, once I've written it down like this, then I can write down what my partition function is in this language. So that's going to be Z sigma of R naught. Well, I'll just call it Z sigma. Make it simpler. It's going to be Z sigma times then the integral dsL prime e to the h s prime, the Hamiltonian for the long wavelength degrees of freedom, and then the term that comes in here, over here on the left-hand side, that term then I can just write as e to the v with respect to my unperturbed Hamiltonian, just like we did in the real space renormalization group. So then what I'm going to do is I'm going to use the cumulative expansion trick to calculate expectation value of e to the v. Okay, so let me just write down exactly what these different terms are, so you have it in your notes. So this term over here is just z sigma, and it's just a function of r naught. This is just the integral d sigma e to the minus 1 over 2v, the sum over lambda over L is less than K is less than lambda, sigma of L and K squared times R naught plus K squared. So that's the thing that we already know how to calculate. And then the factor e to the v, we're going to use the cumulative expansion for that. So we're going to write it down as e to the expectation value of v. And then the next order term, which we anticipate we are going to need, which will look like v squared minus the expectation value of v squared. And then there'll be higher order terms that we are not going to deal with. And so this is exactly analogous to what we did in real space, but now all of these integrals are being done in K space. So let's write down the final answer. So then our partition function, after we've done all this, and we're going to do the calculations in a minute, but let's write down the final result. So that's going to look like the integral d SL prime, and then e to the h s prime, and then e to the expectation value of v, thus 1/2 expectation value of v squared minus v naught squared, like so. And then after we've done this, so let's suppose we now go ahead and do that integral, which is not too hard, but we have to do some work. Then we're going to then set k, L is going to be L times K. So we're going to rescale our wave vector range just as before, and we're going to make SL prime of K be replaced by Z times SL of KL, just as we did before, just as we did for the Gaussian theory. And then once we've done that, once we've done all of those things, then we can then read off the effective Hamiltonian at the scale L. And let me just write down what that's going to be. It's a bit of a mess. So H of L will now be SL of KL, and that's just going to be HS prime, now Hamiltonian, but now S is replaced by Z times SL, the renormalization constant, and then expectation value of V plus 1/2 expectation of V squared minus V all squared. And then when we've written that down, it's going to end up looking like this: 1/2 the integral over K, a function that I'm going to call U2L of K, then SL of K squared plus 1/4 the integral over K1 up to K4, a function that I'm going to call U4L, which is going to depend on K1, K2 up to K4, and then times 2 pi to the d times a momentum conserving delta function, which I will just write as this: I equals 1 to 4 Ki, and then my new fields SK1 up to SK4. So that's what the effective Hamiltonian is going to look like. Now, you might say, well, wait a minute, this doesn't look like the original Hamiltonian at all. We started off with a Hamiltonian R naught plus grad squared and then the quartic term. Now you can see that the coefficient of the quadratic term is actually a whole function. We never had a function before, but now we have a function that's coming in here. So we have now this, and we have this. Now, what we had before was these were just numbers, R naught plus K squared and just U naught. Now, what I'm telling you is that these things are going to end up being big, complicated functions that we're going to have to compute. So what has happened in the renormalization process, what we're going to find is that when we started off with our coupling constants, R naught and U naught, after renormalization, they go to a function called U2 of L, which depends on K, and a function U4L that depends on K1 up to K4. So our problem has got a lot more complicated, and we have to calculate these things, and it requires some work. Now, I'm not going to do those calculations. They are really hard. They're described in most detail in a review article written by Wilson and Kogut in 1973. It's also in my book, at least to some order. Let me tell you what is the result for computing those functions. Luckily, if you work to just order epsilon as 4 minus dimension, these things become simple, but it's not in general true. So let me now tell you what the result is. So the first thing is I want to remind you that we are working in dimension epsilon is 4 minus d. So we're thinking of d as being 3 dimensions, epsilon is equal to 1. But what we're going to be doing is an expansion in epsilon. So even though epsilon is 4 minus d, and maybe d is equal to 3, what we're going to do is we're going to assume that epsilon is much, much less than 1. And then we're going to compute an asymptotic expansion. I'm not going to do this in class, don't worry. An asymptotic expansion in epsilon, and then we're going to extend that to epsilon is equal to 1. So you can do that. There is a principled way to do it, and we're not going to worry about it. So the main thing I want you to think about this is what we are doing is we're assuming that epsilon is equal to 0.01, let's say. Okay, we're doing critical phenomena in 3.99 dimensions. And if your epsilon is allowed to be small, then what you find is the following. For this particular case, then, what you find is that there is the RG recursion relations generate new fixed points. So remember that in Gaussian theory, you have R star equals 0 and U star equals 0. Okay. Now, when we talk about when we do the calculation that we're talking about now, so with the quartic theory, what we'll find is that R star is now definitely different from 0 and by an amount that is of order epsilon, and U star is definitely different from 0 by an amount that is of order epsilon. We're going to see what those things are. And the function U2 star of k turns out to be R star plus k squared plus terms of order epsilon squared. If we look into those terms of order epsilon squared, it's disgusting, so don't look at them. So then we look at U4 at the fixed point. U4 at k is actually U star plus order epsilon squared. If we look at U6, so you might say, well, how do you know that there's only quartic terms? Maybe there's terms of higher order in the Hamiltonian. Yes, there are. We generate those, just as we did in the real space renormalization group. Those extra terms have to have the original symmetry of the Hamiltonian, which was even in powers of s. So therefore, we're not going to get any terms of order s to the fifth, but the next term we will get will be of order s to the sixth. If it's a term of order s to the sixth, it's going to be multiplied by some complicated coupling constant function, which I'll call U star of 6. That term is order epsilon squared, so we don't need to worry about it. If I look at U8, that's order epsilon squared and so on. So basically what I've told you is that as long as I only work to order epsilon, the calculation, even though in principle it's going to be absolutely disgusting, in practice, it's not that bad. Okay, it's still not great, but it's not that bad. Okay, so that's what we're aiming for. All right, now let's talk about the complications that you get in doing the calculation. Okay, so this is this is what we're aiming for. So how do we do the calculation? Okay, so this is now section 12.3.2. So how to calculate the cumulants, the expectation values of V, V squared, and so on. That's where it's all complicated. Okay, I'm going to sketch it out to you, and you're not going to follow it in real time, but you will get the general idea of what we're doing, and that's all I want you to get from this, at least for this first pass through. So here's the thing we're trying to calculate. Here is V, it's 1/4 U naught, the integral K1 up to K4, momentum conserving delta function. And then SK1 to SK4. So that's the thing I want. every time I have an integral, let's say integral of k, s of k, every time I have such an integral, remember that what this means is the following, is the integral from naught to lambda over L dk, d slash dk, so I've got, there's the two pi's in there, SL of k plus the integral from lambda over L to lambda d slash dk of sigma L of k. So what I've got here is when I write down S, I'm going to write that as SL prime plus sigma, and I'm going to write down the terms that you get from doing this. But remember, each of those terms comes with an integral, and the limits on those integrals aren't the same. The limit in one integral is naught to lambda over L. The limits on the other integral are lambda over L is less than lambda. So think what happens then when I take s to the fourth. So when I write down s to the fourth, what that's going to do is it's going to generate terms like this. S prime, S prime, S prime, S prime. Then there's going to be a term that looks like this. 4 S prime sigma, S prime, S prime, like that. Then there's going to be a term which is 6 S prime, S prime, sigma, sigma, and so on and so forth. All the terms that you get in a binomial expansion. Okay, so that's what each one of those quartic terms, when I multiply them together, it gives me this. And now what I have to do is I have to then compute the expectation value of this with respect to the 0th order Hamiltonian for the sigmas, for the short wavelength degrees of freedom. So I'm going to just write down for you now what you get for the terms of order expectation value of V. I'm just going to look at the typical terms. Okay, so that's the strategy. So let's have a look at a typical term. Okay, so I want to look at that. Why do I want to look at that? Let me just go back here. Remember on the left-hand panel, just look over here. On the left-hand panel, the effective Hamiltonian that we're trying to read off, I have to compute expectation value of V, I have to compute expectation value of V squared, I have to compute expectation value of V, and then square the damn thing, okay? So that's why it's going to be messy. So let's have a look at just what one of the terms looks like in that expression. So the term that I'm going to focus on, since it's the kind of the most important one, is this one. I'm going to look at that. I'm going to show you what that looks like. So what that's going to look like, this particular term in that, it's going to look like this. So first of all, my integrals. I got my integral wrong here. Those are the long wavelength parts that go with the S primes. For the short wavelength parts, I have to do this. So this is D slash K3. Same thing, lambda over L to lambda D slash K4. So that's the first thing. Then I need my 2 pi to the D times my momentum conserving delta function, like that. Then, yeah, really stupid idea to start writing this at the bottom of the page, right? I can't believe I did that. Yeah, let me see if I can just move it over here. Okay, great, brilliant. Okay, so I've got that. And then the next thing I'm going to have are the fields. So I'm going to get a field SL prime of K1, SL prime of K2. So that's the first two S's. Then I'm going to get the sigmas, but what I'm computing is the expectation value of V. So what I'm going to have in here is sigma L of K3, sigma L of K4, and then with respect to the short wavelength degrees of freedom Hamiltonian, H0. Okay, so this is something that we have to calculate. And the thing about this is when I do this calculation, you can see that it has, it's a function of two things. It's a function of K3 and it's a function of K4. So you tell me what K3 is, you tell me what K4 is. Space is just a label. Therefore, K space is just a label. So when I tell you this is a function that depends on K3 and K4, the game is you tell me which Fourier components you want. K3 is equal to 17, K4 is 137. Okay, those Fourier components are the ones whose expectation value you are computing. So when you do this integral, once you've done it, it's going to be a big mess, but our big mess is going to be dependent on the function, on the variable K3, K4. When we do that K3 and K4, well, wait a minute, those are dummy variables because they are being integrated over here. So what I do is I do this integral, this expectation value, get a big mess of K3 and K4, then I have to do the integral between K3 and K4 between lambda over L is less than K is less than lambda, conserve momentum with my momentum conserving delta function, and then do the integrals over K1 and K2. So this thing is sort of messes upon messes. So let's suppose I've done this. Let's suppose I've successfully managed to do this. Then what I'm going to have, this is going to lead me to this. I'm going to end up then with U0 over 4, the integral from 0 to lambda over L, two of those, 0 to lambda over L, d slash K1, d slash K2, SL prime K1, SL prime of K2, and then that's going to be multiplied by some function, some mess of K3 and K4, which has then been integrated over K3 and K4 times my momentum conserving delta function. And after I've done all of those integrals, what that's going to end up giving me is a function that will contribute to U2L of K. Why is it going to contribute to U2L of K? Well, because this term, after I've done this, there's just a bunch of stuff which depends on K, but there's only two S fields. There's only two S fields, so it's quadratic in S. So therefore, whatever this function is, it contributes to the function that I called U2L of K. So you can see now that when I said that these functions are complicated, I wasn't joking. That's what they are going to be. Okay. All right. So any questions about the general idea? And then I'm going to show you, I'm going to then skip like 3 weeks and of calculation and tell you what the actual answer is. So do you understand the general idea? Why it's complicated, but it's not, it's just lots of little steps that are complicated, and we just have a bunch of integrals to do. Okay, so everybody is more or less happy, at least as happy as you can be given this sort of skeleton. Okay, so now I'm going to tell you what you get when you do the honest calculation. And you can look through chapter 12 of my book. Here's what you find after you've done all this. This is what you get. U2L, at least to first order in V, so we'll call it U2, first order, is equal to this. R naught L squared plus KL squared. Okay, let's go back to what we did before with the Gaussian theory last time. Okay, remember we did with the Gaussian theory last time? So look over here on the left-hand panel. What we calculated last time was exactly this, and this was the new coefficient of the quadratic term. So we have a term that looks just like that. We have a term that looks just like that, but now we have more complicated terms. So we have that. Then we have a term that you've never seen anything like this before. This is going to be 3 U naught L squared, the integral from lambda over L to lambda d slash k over R naught plus k squared. Okay. And so now you can see that what has happened here is that U naught has come in to the second order term. And we saw that U naught is bound to come into the second order term because I showed you that right up here. This quartic term will have terms that contribute to U2, the coefficient of the quadratic terms. And so you can see what it is, and that's just the integral that you get. And you know enough that you could actually go from the lines above to getting this result. So if you wanted to, everybody in this room could do that calculation. You would have to step through it and think about it and say, what am I really doing here? But you would be able to do that calculation. Okay, so that's great. That's the calculation. We just have to do that integral. Okay, and now you can see that there's going to be R naught and U naught now get mixed together, even at this first order in perturbation theory. Okay, now here comes the next thing. So now let's have a look at what the quartic coupling constant looks like. And this is really kind of a bummer. The quartic coupling constant, when you work it out, looks like this. U naught L to the power 4 minus D, which is U naught L to the epsilon. Okay, now why is this a bummer? Remember when I told you about the general idea of the epsilon expansion, I said, let's try to figure out what's going to happen to the scaling of the quartic coupling constant. And I said, if I just look at the dimensional analysis of it, dimensionally, it's going to go like L to the power 4 minus D, because we worked out what the dimensions of this thing were. So naively, you would say this. And then I said, well, but suppose it were the case that I do this in 4 minus epsilon dimensions. If there was another term that went as epsilon squared, then when I took the logarithm and wrote down the normalization group recursion relation, I would have a non-zero fixed point. If I have just this and I look to see, is there a non-trivial fixed point? The answer is no. The only fixed point is U naught is equal to 0. So this means that going to the first order in perturbation theory is not enough. So this result here, you've seen it before. This is what we guessed. Just based on dimensional analysis. And so we're not going to be able to get any anomalous dimensions out of it. We're not going to get any non-trivial fixed point. And so sadly, we have to do like 1,000,000 times more work than what I just showed you. Okay, so because it's what we guessed from dimensional analysis, it implies no non-trivial fixed point. And it means no anomalous dimensions. or critical exponents. So that means that we have to go to order v squared. Sadly, we have to do that. Okay, all right. So how do we do that? Everything I've shown you for order v is now going to be done to v squared. So you're going to get all these, you're going to get, instead of having 4 terms multiplied together, you're going to get 8 terms multiplied together. All the possible permutations and combinations of s plus sigma, all raised to the power 8th, and then with all the correct coefficients, and then doing all the integrals, okay? It's a lot of work, okay? That's the part where you have to use Feynman diagrams. Okay, so order v squared, that's going to mean that you're going to get s plus sigma to s plus sigma, but there's going to be 8 of them. That implies lots of combinatorics. And that implies that to keep track of the terms, we use Feynman diagrams. And they're all worked out and explained, and all the combinatorics and every single factor is shown in chapter 12 in my book. And I'm not going to do that, okay? Because it's a lot of work. So that's the first thing. We have to use Feynman diagrams to keep track of this. What are Feynman diagrams? All it is saying, if I've got terms in perturbation theory, and I want to make sure I've written down every possible term, then it turns out that there's little diagrams that you can draw that tell you, if I look at this diagram, I can translate it into an integral. So a Feynman diagram is just a shorthand for an integral. So if you say to me, well, how do you do this calculation, Nigel? And I say, well, I just evaluated this term over here, like this. You say, okay, fine, yeah, I know what you mean, okay? Okay, it's like a sort of secret language that people who know it know. There's nothing complicated about it. It's just much easier to write that down than writing a huge, big integral. So you can take this, and then there's rules that tell you how to go from this to the integral. That's all a Feynman diagram is. Okay, so that's the first thing. So that's the strategy we use Feynman diagrams. Now, here's a thing that is true. In these Feynman diagrams, we have terms like this. Integral d dk of some stuff. Okay, right? And what we're going to do, that stuff turns out to be stuff that depends on k squared. And because it depends on k squared, that means that it's rotationally symmetric. So that means that when we do these integrals, we can just do the angular part of the integral. It's just, 4 pi or something like this. So what we're going to do is we're going to replace this integral by the integral of k to the d minus 1 dk times sd, where sd is the surface area of a unit d-dimensional sphere. And there's a beautiful trick for being able to compute that. Okay, so that's just like 4 pi in 3 dimensions, or 2 pi in 2 dimensions. You learned that on your mother's knee. You can work it out. In general, it turns out to be a ratio of gamma functions and things like this. Okay, so what we're going to do then is we're going to treat. So the idea then is that we are going to let me use this color. We're going to treat. We're going to treat this as a continuous variable. if I tell you I've got the function integral dk of k to the d minus 1 times some blah, okay, then it's just an integral that I have to do. D can be anything I like, and I do the integral. At the end of the day, I'll set d equal to 3 or whatever. So that's the trick where we treat d as a continuous real variable. Okay, so now I'm going to tell you what you get after you've done that. Okay, so here's the result. There's nothing intuitive about this result. There's just a big mess. And I'll probably write it down with a typo as well. So, you know, I just want to show you that you can do the calculation. Here is the renormalization group calculation to order epsilon squared. So it looks like this. R prime is L squared times this. R naught plus 3 over 4 pi squared U naught over 4 lambda squared 1 minus 1 over L squared, okay, minus 3 over 2 pi squared U naught over 4 R naught, the logarithm of L, plus terms of order epsilon U naught and higher order terms. That's the term for R prime, and U prime over 4 is equal to L to the power epsilon times U naught over 4 minus 9 over 2 pi squared U naught over 4 squared times the logarithm of L plus order epsilon squared. Oh, and there's I did put a brilliantly bad typo in. Let's take this out. Okay, that's the typo mistake that I made last time. Yeah, it goes in like that. Okay. Yes. Okay. All right. Okay, so that's our renormalization group recursion relation. After all this, that's all we wanted was the recursion relation. What do we do next? We find the fixed points, then we do the linearization and find the exponents. So the first thing is we've got this L to the epsilon. So remember what we do with a thing like L to the epsilon. So L to the epsilon, I could write that as E to the epsilon log L, right? And then I can write that as 1 plus epsilon log L plus 1/2 epsilon squared log squared of L dot, dot, dot. Okay. So then I take that expansion and then plug it into the formula for U prime. And so then when I've done that, then I get, as my RG recursion relations, R prime is equal to, well, L squared stays the same. So R prime stays the same. Don't need to repeat that. But then what I get is that U prime is equal to, I'm guessing this is U prime over 4, is U naught over 4 plus U naught over 4 times epsilon minus 9 over 2 pi squared U naught over 4 times log of L something like that. Hopefully that's correct. So that's my recursion relation. So now it's downhill. So next thing we do is find the fixed points. And you can see that there is a fixed point here to order epsilon. So there's one fixed point. So there's one fixed point, which is R star is equal to U star equals 0. And that fixed point is the same one that we found before, the Gaussian fixed point. But there's another fixed point. That other fixed point is the one where this thing in here is equal to 0. So there's another fixed point, which is U star is equal to, U star over 4 is equal to 2 pi squared over 9 times epsilon. Okay, so that's a non-trivial fixed point. And then the corresponding R star is equal to minus epsilon lambda squared over 6. So I find the U star fixed point, then I put that in here for the R prime, find the fixed point, and so I get this thing. And this result has a name. This is known as the Wilson-Fisher fixed point. Okay, so the fixed point does not depend on L, but it does depend on my coarse graining scale, and there's nothing wrong with that. Then now what we do is we linearize around the fixed point, and then compute the linearized normalization group transformation. So what you end up with is, so this matrix M, just like we had before, it's basically dr prime by dr, dr prime by du, du prime by dr, du prime by du. That matrix with all of those derivatives evaluated at the fixed point. And we can do this at the Gaussian fixed point. We can do this at the Wilson-Fisher fixed point. So let me tell you what it looks like. So then what you find is that M Gaussian is equal to this matrix, L squared 3 lambda squared L squared minus 1 over 4 pi squared naught L to the epsilon. And the matrix for the Wilson-Fisher fixed point looks like L to the 2 minus epsilon over 3 lambda squared L squared minus 1 over 4 pi squared naught L to the minus epsilon. Okay, so now what you do is you take those matrices and then you compute the eigenvalues. So you compute the eigenvalues. So for the Gaussian fixed point, it simply is that lambda t is equal to L squared, which means that yt is equal to 2. And lambda 2, there's another eigenvalue, which is L to the epsilon. That implies that y2 is equal to epsilon. Right, that's the Gaussian one. I'll talk about what all this means in a second. And then the Wilson-Fisher fixed point is I get that L at the lambda t goes like L to the power 2 minus epsilon over 3. And that means that y sub t is equal to 2 into 1 minus epsilon over 6. And I have a second g eigenvalue, L to the minus epsilon, which implies that y2 is equal to minus epsilon. Okay, so those are the eigenvalues. Not quite the exponents. I need to finish, so I'll take your question later. So the thing you'll notice is that the matrix is not symmetric. And so the eigenvalues are not orthogonal. And if I compute the matrices M times the eigenvectors is equal to some eigenvalues times V, then the eigenvectors turn out to be something like this. R is R U naught over 4, and the eigenvectors look like this. So I'm going to draw an axis. I'm just going to sketch it. I'm not going to write down the formula. So here is U naught over 4. Here is R. And what I'm going to draw for you is this twice. I'm going to draw this twice for you, once for d greater than 4, which means epsilon is negative, and once for d less than 4, which means epsilon is positive. All right, so and again, I'll probably end up confusing them. So let's make sure I don't do that. So here is the eigenvectors. One looks like that. One looks like this. So the flow looks like so. So in this picture, d greater than 4, U naught is negative. This is the origin over here. And so that's not a physical thing. So what happens is for d greater than 4, you just have the Gaussian fixed point. On the other hand, when you have d less than 4, then what you have is you have your Gaussian fixed point still at the origin as usual, but now you have the Wilson-Fisher fixed point is up here, and the flow direction looks like this. And this here is the Wilson-Fisher fixed point. And now this is unphysical. So that one doesn't count, but this one is physical. And this is the thing that controls the critical exponents. Okay, so when you go ahead and do the calculation, so now you have that. Now you can do the calculation. And what you find is for d less than 4, the critical exponent nu is equal to 1/2 into 1 plus epsilon over 6 plus order epsilon squared. And you find that gamma is equal to 1 plus epsilon over 6. Beta is equal to 1/2 minus epsilon over 6. Eta is order epsilon squared. Alpha is equal to epsilon over 6. And delta is equal to 3 plus epsilon. And if you then plug in epsilon equals 1, then these results are closer to the numerical results than mean field theory, and they can be systematically improved. So the basic program that we laid out in real space we did it in momentum space. There was a lot of steps and a lot of combinatorics, but conceptually, it was still just Kazanov block spins, coarse graining out the small wavelengths degrees of freedom, renormalizing, reading off the functions and doing a lot of calculation, doing the eigenvalues, reading off the critical exponents that way. So that's where I'm going to stop. So now you've learned the basic idea of a normalization group. Of course, you can't do the calculation because it's a lot of work. You can, if you want to learn how to do it, read chapter 12 of my book. If you want some exercises to do the homework problems in chapter 12 of my book. If you want to talk about it with some more with me, those of you who are interested in the field theory aspects of this, feel free to talk to me about it. But this gives you an overview of this. Hopefully now, if you go to a seminar and anybody intimidates you by showing you Feynman diagrams and the normalization group and stuff like that, you'll know that basically, conceptually, it's not that complicated. There's some technically complicated algebra, some math tricks and so on, but hopefully you've got the general idea of what is going on. Okay, so that's where I'm going to stop. We have one more lecture left, Thursday's lecture. So Thursday's lecture, I promised you I would give you a lecture about the phase transition to turbulence using the normalization group and all that. So I'd like to do that. I did notice that there is a slight conflict. Well, for some of you may want to do this. We have this week on campus the Kyoto Prize Week. Have you heard of that, the Kyoto Prize? It's like the Nobel Prize for Japan, okay? And it is given in Japan, in Kyoto, last November. And for various reasons that are not clear to me, it is mirrored over here in San Diego. And is also mirrored in Oxford University in England. They do the same thing. All the people who won the Kyoto Prize come here and they give public lectures. The winner of in the field that you might be interested in is Shunichi Amari, who is a Japanese professor who figured out the first sort of neural network with associative memory 10 years before John Hopfield did. His version was slightly different, but definitely same kind of thing. Some people think he should have got the Nobel Prize too. He's got the Kyoto Prize for this year. So he's going to be on campus and will be giving 2 talks about his work about AI using physics to develop these very early AIs in the 1970s and 1980s. So I definitely encourage you, if you have not done so, to go to the website, look for UCSD Kyoto Prize, sign up to see those talks for those of you who are interested in machine learning and so on. It'll be a very unique, never to be repeated opportunity to meet one of the seminal founders of AI and machine learning. Okay, so that clashes, one of the lectures clashes with this class. If I decide to cancel my lecture on phase transitions in fluid mechanics to go to that lecture, I will let you know, and I will give you that lecture at another time so that you can still have that lecture. So please, if you want to go to his lecture, please send me a message, because if half the class says, okay, we're going to go to this, why would we listen to you talking about your stuff? We'll go and listen to him. Okay, that should be your natural reaction. Okay, then I will just cancel that last lecture and do it later. Okay, so it's 5 to 2, so we have to get out of here. I'll take questions afterwards. Okay, so I'll take questions outside, and I have to exit the classroom. So let me turn off the recording.